Hi, I'm Michael Drinnan. Welcome to this series of lectures on clinical instrumentation and digital signal processing. I guess doing things this way is new for all of us, and so please bear with me. And if you have any questions, suggestions, anything you would like to ask, feel free to contact me. We normally do this session in person and with a little bit of audience participation, but we are where we are. You all know why things are like this, and so welcome to my kitchen. First of all, I'll say a little bit about the equipment we have around. So we're going to be talking about physiological signals, and those are signals that we record from the human body. And so the first thing I've got here is a signal generator. A little bit later on, we'll be recording signals from volunteers, which will probably be me. And the other thing to take notice of is this instrument here, which is called an oscilloscope. So you might be familiar with chart recorders. This is really just an electronic version of the chart recorder. The signal generator is generating a signal, which we'll talk a little bit about in a minute, and the signal is being displayed on the oscilloscope. Up here somewhere, you'll be able to see in a picture-in-picture an expanded view of what's on the oscilloscope at the moment, just so you can see a little bit better what's going on. A signal, in its broadest sense, is just something that we can measure. And generally, we call it a signal because we think it's telling us something about the world. That would normally imply that the signal was changing, because if it never changed, like a clock that had stopped, it wouldn't be telling you anything. So if you look at the signal that's displayed on the screen now, this in some respects is the very simplest type of signal for reasons that we'll get into later. And we will call it a sine wave or a sinusoid. If you look around you, you'll see this shape of signal in lots and lots of places around the world. So if you want to describe the heights of the tides, the transition between daylight hours and nighttime hours through the course of the year, if you look at how a guitar string vibrates, all of those are displayed by a signal that looks a little bit like this. Some go faster, some go slower, but broadly the shape is the same. If I asked you to describe this signal, probably the first thing you would comment on is its regularity. This waveform clearly is repeating something like once every second. And so the first thing that can change about a signal, the first thing that we might be interested in, is its period, or to look at it the other way, its frequency. If I adjust this control on the signal generator, you'll see I can speed the signal up. We probably should just adjust the control on the oscilloscope here so that it can catch up. And you may just about be able to hear that there's something coming out of the loudspeaker. So up until now, it's been a slow signal, maybe once or two or three repeats every second. And that's at too low a frequency for our ears to hear. But as I increase the frequency some more, you'll notice that the pitch changes. If I adjust this control, you can see that I can make the signal larger or smaller. We will call that the amplitude. Amplitude, in terms of sound, is what we perceive as loudness, intensity. So frequency and amplitude are two properties of a signal, of a sound signal, that directly link to something that we can hear. Now, this may seem like a very simple example, but actually sound, it's not completely irrelevant, as we'll come to see. You might think about things like your doctor listening through the stethoscope, and there are other situations, and we'll give a demonstration of that a little bit later, of where sound is actually used in the diagnostic process. So sound itself can be a physiological signal. But the reason it's useful here is because we can all hear sound, and so a lot of the points that we're going to make are very well made by listening. There is one other property of this signal that I'll say a little bit more about now, and we've already mentioned the shape of the waveform. What we see on the screen at the moment is a sinusoid, a sine wave. It has a very pure sound to it. It sounds a little bit like a flute, perhaps an organ pipe, very pure tone. If I change the shape from the sine wave to what we would now call a square wave, you can probably hear that the pitch hasn't changed, so it's the same note, the same musical note, but the quality of the sound has changed. It sounds much more electronic now. If I switch back, sine wave, square wave. And so it's apparent that even to our ear, the shape of the waveform, as well as its amplitude and as well as its pitch, tell us something about what we hear. And we might imagine that it tells us something about whatever it is that's causing that signal. And so maybe the shape of the waveform is going to tell us something about the physiology of the human that's creating it.